Okay, so in the last class we had been looking at the HSB system for representing color, where we had hue, saturation, and brightness. Hue is typically represented as a point on the circumference of a circle, so it goes from 0 to 360 degrees. Saturation is usually represented as a point on the radius of that circle, goes from 0 to 100%, and brightness is on a separate axis, again from 0 to 100%. The hue is connected to the frequency or wavelength of the color. The saturation tells us how pure the color is, and brightness tells us how light or dark it is. And that's by far the most natural system for humans. The RGB system, on the other hand, is used in computer systems. We have a value that tells us how much red is in the color, a value that tells us how much green is in the color, and a value that tells us how much blue is in the color. And these range from 0 to 255 each, mostly just because that's 8 bits worth, and that's handy. And we're going to look at two more now, and then we're going to look at, once we've got to grips with the whole way of representing color, we'll start looking at how images themselves are represented. So, two more systems we want to look at. That's an RGB. There's the LAB system. And this is of interest for two reasons. The main reason you might ever have bothered with the LAB system is that it was connected quite closely to the way analog television worked. Now, analog television hasn't changed the way it works. It's just analog television is a past tense thing now. And another reason you might be interested in the LAB system is because it can be used to exploit some of the properties of human vision. And we'll look at those. So that's why we're interested in it. You won't ever use it, probably. You won't ever come across an image that's saved this way, probably. So the LAB system, again, has 3 values. And you can't represent color with less than 3. You do need 3 values. And there's the luminance and the chrominance information are separated out from each other. Now, the luminance is how light or dark something is. And chrominance then is the color information. We're told that dogs and cows can't see color. They can only see light and dark. So we might conclude that, or we could say that they're not sensitive to chrominance information, just luminance information. So with the LAB system, the luminance is represented in this L value, and that tells you how light or dark the color is. And then the color, so to speak, is represented by 2 values, A and B. So A ranges from like the green end of the scale to the red end, and then B ranges from green to blue. So in theory, all of the different possible colors are in there in that box. And it's just a question then of them being light or dark. So when an image is stored in this color space, it does have a very interesting property. If you consider here an RGB image, if you wanted to make a black and white version of an RGB image, you'd have to take the red value of each pixel, the green value of each pixel, and the blue value of each pixel, and average them out to get how bright something is. and there's work involved in that. Whereas to get a black and white version of an LAB image, you can just ignore the color information. So in the L channel, you have a black and white version of the image, and then the A and B channels provide you the extra information you'd need to turn that into a color image. Could you close that door there, actually?
Yeah.
Thanks. And analog television used something quite like this in order to seamlessly accommodate the transition from black and white to color. So people were watching black and white television signals on black and white televisions, and then we decided we were going to have color TV. And one approach would be to have color television channels for color televisions, along with black and white channels for black and white televisions. But then you would have needed, like, two of each channel. And so engineers came up with a clever scheme to continue broadcasting television in black and white, and then to supplement that information with what was needed to generate color television. So the people with just black and white TV could carry on watching the black and white stuff, and then people watching color would take the black and white signal and the extra information to make the color. Now, I've oversimplified there hugely, but that allowed backwards compatibility between color TV and black and white TV. Now, when I say TV, I mean ye olde cathode ray tube that you had when you were very, very small. There's very little of that television left around the world. Ironically, you'd probably find it in Cuba, all right. This was photographed. No. So, if you have an image in LAB format, if it's stored that way, and you just want a black and white version of it, well, you could just take the the L values and ignore the A and the B, and you've got a perfectly serviceable black and white version. What's interesting, though, is that humans really suck at seeing color, actually. We're very sensitive to subtle changes in luminance. But chrominance, we're not so good. There may be other species that are much more sensitive to chrominance than us. It's hard to know because you can't do experiments on them all, obviously, and they can't tell us. But in the grand scheme of things, compared to our sensitivity to luminance, humans aren't very good at chrominance. So, for example, if you get up in the middle of the night and it's dark, you can see in the dark, but you can't see color in the dark. And we can detect differences in subtle changes in the brightness of something, subtle changes in color, not so much. And this is a property we can exploit. So I don't think I spoke about subsampling before, but subsampling is where you reduce the amount of information you have to deal with by throwing a lot of it away. So you might decide for a particular module, there are too many notes to read before the exam. I'm just going to read every fourth page. And that might be a perfectly reasonable strategy. I actually have a friend who went, when he's East German, he went to get his Stasi file, and you could only get so many pages free. You could only copy so many pages free. You had to pay after that. So he just went and copied every 10th page. He just subsampled it. So you can do things like that. So you can reduce the amount of information you have to deal with by literally just throwing stuff away. And what JPEG does is, it's very clever. It separates out the luminance and the chrominance parts of the image, leaves the luminance part intact because we're quite sensitive to that, and throws away shed loads of color information, and we kind of get away with it. And I'm going to show you, I've simulated an example of that. So here's a picture of me, and if this is 400 pixels by 400 pixels, and there's 3 bytes per pixel. There's 3 bytes per pixel because it's 24-bit color. So each pixel is stored in RGB, so 24 bits per pixel. Now, what I did was I brought this into Photoshop and converted it to LAB. So it was still 24 bits per pixel, 8 bits for the L, 8 bits for the A, and 8 bits for the B. And then I subsampled the chrominance parts, the A and the B parts. So basically, instead of so the image is 400 pixels by 400 pixels. Here what you're seeing is the luminance at 400 pixels by 400 pixels, but the chrominance is actually 100 pixels by 100 pixels. So the color information in this has been reduced. I've thrown away 15/16 of the color information. The color information in this image takes up only 1/16 of what it did before. So that's a lot. I was being very dramatic, pushing the boat out, throwing a lot of it away. And you can see the image is actually not so bad. It doesn't look that bad at all jokes aside. So, I mean, if this was a picture of Carnival in Brazil, you know, because that was last night, then if you threw away 15/16 of the color information, you might notice, perhaps. But it's not a very colorful picture anyway. So the one on the left there, if it was stored without any kind of compression or anything, would take up 48,000 bytes. And the one on the right, in which the luminance has remained intact, so that was the 160,000 comes from there, but the chrominance information has been reduced dramatically. And so it's about a third of the size. And it's not that bad. Do you know? I mean, if you were sending this somewhere and said you could spend €3 to send the first one, or €1.10, whatever, to send the one on the right, you might send the one on the right and keep the rest of the money for something else. Can anybody see where it starts to go? Can anybody see where it's a bit dodgy? Anybody spot the difference? That you're not all jumping out of your seats now and shouting kind of makes my point that we're not very sensitive to shabby color coding to the same extent that we are if we fiddle with the luminance. Can anybody see where it's kind of obvious? If you look there behind the red space invaders, the color is a bit off. Can you see it now if I go back? The color is slightly off. And I think that's the only thing. I suspect maybe if you zoomed in on the tie, you might find that the stripes aren't perfectly stripy. You know, that might be another place you'd see it. But for the most part, you know, that was a good deal. Got away with that. In this image, I've done the exact same thing with the luminance component. I reduced it in the same way. And it's very noticeable, isn't it? And in actual fact, even this would only be 2/3 of the, this was a third of the size, roughly, of the original. This would actually be 2/3 of the size of the original, roughly. But because I went messing with the luminance component, it's really noticeable. Whereas if you go messing with the chrominance, you might get away with it. So that's one of the things that JPEG does that lets it reduce the size of files. And you can simulate that. I might make you do that later in the lab. You can simulate that in Photoshop if you convert something to the LAB and then reduce the quality of the A and B components. That'd be a good experiment to do with your pictures, and then you could include that in your report. Great plan. I love it. No. So that's why we're interested in LAB, because it illustrates that property that we're interested in. You won't typically deal with LAB as a color system. The last one then that we need to look at, just for completeness, is the CMYK system. And that stands for cyan, magenta, yellow, and black. Do these colors look familiar to anyone? When you go to the shop to get ink for your printer, that's what you buy.
Any package has a test pattern.
Yeah, and you notice that on packaging or on the newspaper, you'll sometimes see boxes with those colors. And that's the printer checking that everything is in order. The cyan should be perfectly cyan, the magenta should be perfectly magenta, the yellow should be perfectly yellow, and the black should be perfectly black. You might even see black at different ratios, 10, 20, 30, 40, 50, 60, 70, 80. Next time you get a colour newspaper, look for that. And you'll also see these colour combinations then as well. So the CMYK system is subtractive. The more you add, the darker it gets. I think it's possible that in a mathematically perfect world, if you mix the cyan, magenta, and yellow together, you might get the black. And you might be able to do without black ink. But, for practical reasons, we use it. First of all, it's cheaper, and most of the time, if you printed the text in your newspaper using the cyan, magenta, and yellow, it might not look as good as if it's just plain black. But I think theoretically, at least, it may be possible to devise a scheme if everything was working right. Okay? The higher the values, the darker the colors get. So we're talking about adding ink to a white page. So the color is usually expressed as a percentage. So if you have like 0 cyan, 0 yellow, 0 magenta, and 0 black, well, that's white, because it's a white page with no ink on it. If you have 0 cyan, 0 yellow, 0 magenta, and 100% black, well, you're looking at black. And then when you come to combine colors, it's kind of familiar because it behaves like it did when you were a kid mixing paints in school or at home. So if you want green, you get blue and yellow, you mix them together, you get green. Which is very different to how you get green in the RGB system. The RGB system is additive. The more you pile in there, the brighter it gets, the closer it tends towards white. The CMYK system is subtractive. The more you throw in there, the closer it gets to black. If you take all the paint pots in your, that came with your colouring book, and you mix them all together, you probably just get some mucky colour. But at least we have a handle on it because we did it as kids. So if you have 50% cyan, which is a kind of blue, and 50% yellow, and 0 magenta, 0 black, you get a shade of green. So this is the system we use in printing, and we represent the values 0 to 100. So if you're 100% cyan, kind of obvious that that's going to be that colour. 100% magenta and nothing else, going to be magenta. 100% yellow and nothing else, going to be yellow. And 100% black and nothing else, going to be black. Go figure. As we've seen, if you mix blue, which is cyan, and yellow together, you'll get some green. Throw in some black there and you'll make it dark green. If you've no colour inks and just black, well then depending on how much black you have will determine what shade of grey you have. If you have a high K value, it's going to be a dark grey. If you have a low K value, it's going to be a light grey. Which if you think about it is the opposite of what we saw in the RGB system. The higher the values, the lighter it got. And mixing magenta and yellow there, we have 0 cyan, 83% magenta, 81% yellow, and a small bit of black. I'm surprised that colour wasn't more orangey. I was expecting that to be more yellowy orange, where it's actually quite red. 0 cyan, tiny bit of magenta, a lot of yellow. We've got that shade of yellow there. If you have 20% cyan, 19% magenta, tiny bit of black. Again, I would have expected that to be a little bit darker. It's quite bright. And then I think pink is always a good test of a color system, see if you understand it. 0 cyan, 30% magenta, 20% yellow, and no black there. So we've got a red, but we're not very committed to it. Which if you think about, if you have red paint and it's fairly watery, when it dries it'll be a pink. Okay. Now, when it comes to specifying color, different industries use different schemes. So in the CIT style book, if you look it up, the style manual for CIT's corporate identity, that CIT red, which I think is very close to pink if you ask me, that CIT red, it will say to you, if you're designing something for the screen, so if it's a web page or a video or a YouTube video or Shockwave or something that's going to be on a computer screen, that color red is these RGB values. However, if you're printing a brochure or printing a poster or printing something, that color red has these CMYK values. You can actually do some maths to convert from RGB to CMYK. So, but if you were ordering something printed, you specify using CMYK. In some industries, the specification of color is very important. So if, let's say Zara is making a dress and the top part of the dress gets made in Morocco and the bottom part of the dress gets made in Portugal, and they ship them both back to Spain and stitch them together to make a dress, well, they'd better be the same color, like. So they would have specified to the factory in Morocco and the factory in Portugal exactly what shade of whatever pink it was going to be. And for some people, the specification of color is really, really important. And there's a whole industry around color specification and color calibration. You often notice when I was going through these things, I kept looking at the screen. And it's like I have a screen in front of me. But my screen here and this projector, when it's black on white, it's not a big deal. But when you're talking about color, there are very subtle differences. And in some of the classrooms, the projector is completely bollocksed. And there's no, like in one class, there was no red at all in it. So when you looked at, the RGB thing, way back here now, sorry. When you looked at the couldn't be arsed. When you looked at the RGB thing, all you saw was two circles intersecting. There was no red at all. So that's a problem. From display to display, the color might be off. So let's say my screen here was very, very dark and I was making a picture for a web page. I might go into Photoshop and I may make it nice and bright and really, really good looking. But then when someone looks at it on their screen, that's okay. They might be blown away by how bright it is because actually my screen was manky and theirs was working. So there's a problem there of calibration. So one of the reasons, for example, one of the many reasons that design people would use Macs is that they can have greater confidence in the calibration of the screen. So that CIT red is always going to look the same everywhere. You can even get things that clamp onto your screen and you run a program and it adjusts it so that it's like calibrated properly, it's standard. If you were, say you're a designer for Zara and you're off on your holidays in Italy and you see a wall, that's kind of a nice rusty orange, something like that, say, and you go, oh my God, I must have that orange. That orange is like the next black, right? You probably wouldn't even take a picture of it. Somebody in that business would have one of these yolks that you can buy, and you hold it up to a color, and you press the button, and it'll tell you the RGB value of this is whatever, the CMYK value of this is whatever, and it'll probably tell you one other thing as well. So if you wanted then to specify that color to someone, you'd have the actual values. So there's a lot of color technology in the world. I mean, for us, I need to buy a black shirt, need to buy a red shirt, whatever, it's not a big deal. But if you're in the color business, if you're in a business where it's really, really important, you need to be specific. So this company here, AGT7, they do something. They obviously work in, they produce something for color professionals. And they had this ad campaign, which I thought was quite clever, where they're like, for some people, black isn't enough. You have to be very, very specific about your color. So so the people reading the magazine that this appeared in, would have known that C0, M0, Y0, K100 was black. Now, looking at it, you would probably guess that anyway if you didn't know. This was another one that I liked. So not just orange, but C0, M60, Y90, K0. A very, very exact shade of orange. And finally then, so C0, M90, Y100 is what? Red, obviously. And you can see, I showed you already that if you were in PowerPoint or any of these things, you can look at the color picker and see the different colors. Let's just see there actually, if we go and look here. So this was HSB sliders. You can look at them RGB as well. We're interested in CMYK at the moment. So C5, M90, Y100, and K0 is a shade of red. Which, as it happens, isn't the same shade of red in that book. And the reason for that is that I scanned that from a magazine. And in the scanning process, I changed the color. So I didn't have my kit calibrated properly. Now, you can also see that the RGB equivalent of that, what do you think the RGB equivalent of that red might be? What's the red value going to be? High or low? High, yeah. And the green and the blue values? Fairly low. Is it a bright red or a dark red? So be kind of low. So, well, I won't be courting disaster now if I hazard a guess. So, okay, 210, so it's quite a high red value. Okay. So that's the RGB values for that color. These are the CMYK values, and these are the HSB values. So if you're specifying the color to a web page designer or a TV person who someone is producing something for the screen, you specify using RGB. If it's going to be printed, you specify using CMYK. If you gave them the LAB values, they'd be what? And HSV values, no one uses those really. No. As it turns out, that Zara designer up the mountain in Italy, the yoke he'd have in his pocket would tell him the RGB value, the CMYK value, and would also probably say, and that's Pantone Orange 74 or something. Have you heard of Pantone? So that's a company that specializes in color. So if he was on to the factory in Morocco saying, I want, 5,000 t-shirts in orange, he'd be saying, and I want them in Pantone Orange, what did I say? 74 or something. Okay? And then that factory would look up its recipe book for colors and would know how to make Pantone Orange 74. When the t-shirts come off the production line, they'd get out a swatch and they could actually check, that it was, their quality control would check that it was the same color. So I have a chair in my house the exact same color as that bag, and I'm pretty sure they didn't, IKEA didn't make them in the same place. But IKEA said, I want, so many thousand bags in that color, and I want so many chairs in the same color. So there's a whole industry built around specifying color for people who need to have precision when it comes to color. Okay. So when you're out shopping, you'll never tell someone again you got a red dress. You'll be more specific. No. So now that we've sorted out how we might represent color, which as we know is a bit more complex than representing black and white images, or black and white color, we're going to look now at how images themselves might work. And we already saw this, did we not? Okay, just checking. So, we're going to think now about how we might compress images. So, like I said before, compression is a reversible conversion of data to a format that requires fewer bits. I explained that already, didn't I? And I folded up my little piece of paper. And we can do quite a number of things to reduce the size of an image. Quite harshly, one of the things we can do is throw some of it away. So when you talk to people about recycling, they say, "I don't know, it's not about recycling. First thing you have to do is you have to reduce the amount of things you produce, to reduce the amount of waste. Then you have to reuse as many things as you can. And only then do you think about recycling." And if we think about some of the complex compression algorithms as being recycling, well, it turns out that when we're coding images, we can do a lot of reducing. We can actually just reduce the amount of data quite a bit. And when it comes actually to compressing video, we can actually reuse an awful lot, as it turns out. So one of the simplest ways to reduce the number of bits required to store some information is to basically throw a lot of it away. So like I said, if you can't possibly carry all your notes around, you might throw away 3 out of every 4 pages. So then it only takes up a quarter of the size. Now, of course, that's quite a good example, because a very careless way to do that might be just, start at the start and throw away, keep 1, throw away 3, keep 1, throw away 3, keep 1, throw away 3. But a good student who could only keep a quarter of his notes might actually look at each page and decide which pages have the most important information. And that's something that we might do. So as we saw with the L and the A and the B, the important information was in the luminance, and the least important information was in the chrominance. So we kept all the luminance information and threw away a lot of the chrominance information. And we're going to see a lot of things like that. So if you have an audio file, for example, or we saw when we were looking at thermometers, we had the temperature for every day. Well, if that's too much information, you could just throw half of it away. Now, that's fairly blunt, but yip-de-doo, it's now half the size. We can do the same with pixels. If we decided there was just too many pixels in this image, or this image was too big, well, sure, look, we'd throw away loads of it. So if we threw away every second row of pixels and every second column of pixels, we'd have reduced the size by 75%. It would only be 1/4 of what it was before. So we just say, bye-bye pixels. So now we've many fewer pixels. So what do you do then at the other end? So I was going to send an image that was 400 pixels by 400 pixels. There was a space waiting over there and all on someone's, mantelpiece for an image 400 pixels by 400 pixels. And when it arrived, it was only 100 pixels by 100 pixels. 3/4 of them were gone. Well, what do you do? There are two things you can do. You could increase the size of the pixels you've got, so now they're twice as big. Or you could interpolate the missing pixels. And depending on which you do, you can have different results. So the larger pixels would be visible. And I think you see this a lot actually in shopping centres and stuff. People download an image off the web and then put it into a huge, giant poster. And it's like, ugh, because, you just got these huge pixels. I mean, if you take a picture on, a crappy phone and then, blow it up the size of a wall, well, you're going to see big pixels. Interpolation is another approach. And with interpolation, what you do is you have a guess at what the missing pixels might have looked like. You give it a lash. In this example here, I've really now subsampled it an awful lot. So we have the original image on the left, and this man is guarding the Portuguese Parliament. And on the right there, this image has been subsampled, and so when it's displayed, it's being displayed then with very big pixels. In this example, the same amount of information has been removed, but here, instead of using big pixels, the missing pixels have been interpolated. So those are kind of your choices. You get big chunky pixels, or you get blurry image. Interpolation works by considering the values of the missing pixels' neighbors. So we have lots of blank spaces here. What might we expect those pixels to look like? I mean, if we look up here, I think it would be fairly clear that if this is green and this is green, then this is probably the same color green here. And if this is green and this is green, this is probably the same color. If this is green and this is green, then the one in between was probably the same shade of green. And if this was green and this was green, then this was probably the same shade of green. And the one in the middle there was probably the same shade of green as well. So we might be doing very well there. At the boundaries of things, though, it becomes a bit unsatisfactory, because you just have to have a guess. So let's look at this pixel here. What might that missing pixel be? So if we just consider now this missing pixel in here, let's take a closer look. What value would it have? What color might we expect it to be? Well, if we consider the RGB values of its neighbors, then we could have a stab at guessing what its RGB values might be. It would be the average of its neighbors. Now, if they were all the same, yip-de-doo, we're probably right. It's probably a patch of plain color, and the missing bits would fit in quite nicely. If it's at the boundary of something, though, that's where the blurriness would come from. So how do you think this might work? What time is it? No, I won't make you do it. Okay, So the average redness of those 4 pixels turns out to be 138. The average greenness turns out to be 157. And the average blueness turns out to be 184, I hope. And that color is in fact that, which looks right to me. You know, that looks to me like the right mix of light blue and dark blue and grey. Everybody understand where that came from? So you're missing pixels, you try and make them up. Have a guess what they might be. So if we go back, say, to the temperature day by day, and you have a graph of the temperatures, and you had the temperature on the 1st and the 2nd and the 3rd and the 4th and the 5th and the 6th and the 7th and the 8th of July, and then that information was subsampled, and every second sample was thrown away, and now you only have the temperature on the 1st and the 3rd and the 5th and the 7th and the 9th and the 11th. And then someone says, oh, you were recording the temperatures in Cork for that year. Can you tell me what the temperature was on the 2nd of July? And you go back and you don't have the temperature for the 2nd of July. You have the temperature for the 1st and the 3rd. And if on the 1st of July it was 10 degrees, and on the 3rd of July it was 12 degrees, you might say, well, look, I'll split the difference. My answer is on the 2nd of July it was 11 degrees. Which is a reasonable enough guess. So you don't have the sample you're looking for, you get the average of its neighbours and give it a lash. Now, in reality, interpolation is actually much more complex than that. If you have an image that is 400 pixels by 400 pixels and you reduce it to 200 by 200, so you're losing every second column and every second row, it's just a question then of putting back in the missing ones. But it's rare that things would line up like that so neatly. In reality, if you're writing code that would do interpolation, you need to handle a situation where it goes from 100 by 100 to 120 by 120. So you need to find one extra pixel for every 4 pixels. Well, no, every 5 pixels. So you have sort of fractions of pixels and stuff. So I didn't want to explode your heads now with that. I didn't want to have to do the maths either myself. But you could see how you could do the maths for that. You'd have weighted averages, and so in this case, for example, you know, it's this plus this plus this plus this. They're all weighted equally. But if you have a pixel that's sort of going to land, you know, in position sort of platform, you know, what is it, platform 6 3, was Harry Potter, what was the platform there? 9 3/4. Like, if you have pixel 9 3/4, you know, how do you do the maths for that? But with interpolation, that's the kind of thing you have to consider, like you've got kind of fractions involved in there and stuff. You know, I mean, so if you go from this, say, 100 by 400 to 120 by, you know, 500, there's an issue going on there. Or if you stretch it across, you know, all that could happen. So interpolation is a bit more complex than I've led you to believe, but that's the idea. You're missing pixels, you try and guess what they are. Okay? So I'm just going to preview now what we're going to look at in the next class. As I mentioned before, and when we looked at black and white images, You can reduce the amount of data by reducing the number of samples, and you can also reduce the precision of each sample. Two things going on there. If we have an image that uses 24-bit color, then in that 24 bits we have the possibility of 16 million and change colors. Do we really need 16 million colors in our image? Would 15 million do? Would 15,000 do? Would 15 do? It depends really on the image. And so if we could figure out a way of reducing the number of colors we need, we can maybe use less bits for each pixel. And so that's called pixel depth reduction. So instead of storing images at 24 bits per pixel, we reduce the number of colors, and then we can reduce the number of bits we use for each pixel. And so if we look here, we have an image that's possibly using 24-bit color. Now obviously this is a fairly contrived example. Suppose we decided we were going to represent that using just 2 colors, or 4 colors. We say 2 bits, 4 colors. Well, we'd do something like this. We would have a palette, we call it, of 4 different colors. And then we would force each pixel in the image to be one of these 4. So it's its closest match. So the lightest colors would all force to be the one on the left. The darkest greens would all be forced to be the one on the right. And so we get this banding here. But now we have only 4 colors and we only need 2 bits for each pixel. So we're going to look in the next class at how a scheme like this would work in practice. Any questions on anything today? Okay, great stuff, guys. Thank you.